we're going to look at section 4.8, which is quadratic inequalities. The first part of quadratic inequalities is just graphing a quadratic inequality. So here we're going to use very similar steps to graphing quadratics in general. So remember, we're going to have a parabola as our shape, but for inequalities, we are going to have dotted and solid boundary curves and shading involved. So I'm going to do the odds throughout this assignment, and you'll be asked to finish all of the evens. So for number 1, when we are graphing, again, we're just going to graph like any old parabola. So since this is in standard form, we're going to go find our axis of symmetry, which is x equals negative b all over 2a. This gives us negative 2 all over 2, so x equals negative 1. From there, I will go find my vertex by plugging in the negative 1. So we'll get negative 1 squared plus 2 times negative 1 plus 1. This gives me 1 minus 2 plus 1, which gives me 0. So at this case, we have the vertex of negative 1, 0. So now let's plot that. Negative 1, 0 is here. And we are going to notice we have an a value of 1 that's positive, so we'll just go up 1 over 1. And again, from my vertex, we'll go up 4 over 2. So we have our parabola shape here, but now what we need to do is make sure that we use a dotted or solid curve. Since it's just a greater than, that means we will have a dotted curve. Make sure to extend that. Don't just have a short little u, because we're going to have shading. So we need to make sure to have our graph be large enough. So at this point, we're going to use our test point to figure out our shading. I'm just going to use the origin because, again, the origin is not on my curve. So this would be saying, is 0 greater than 0 squared plus 2 times 0 plus 1. Again, I'm taking the test point of 0, 0, plugging it into the inequality. And this is 0 greater than 1, false. So that means the origin is not part of our solution. So our shading is everything within the parabola. So there is the graph. If I asked what some solutions would be, it would be any ordered pairs in that shaded region. Okay, you try number 2. Again, it's in standard form, so you can find your axis of symmetry vertex, graph that curve, watch for dotted or solid, and then use a test point for shading. Now we actually want to solve these quadratic inequalities. So we have 2 methods, solving by graphing and then solving algebraically. So for solving by graphing, you can always refer back to this page of the notes, okay? When we're solving by graphing, what we're really looking at is which x values, so not which ordered pairs, but which x values will make the statement true. So if I have a quadratic equation that's going to be less than 0, then what I'm focusing on is when is that parabola actually in the negative range, right? If I'm less than 0, it's saying when are my y values less than 0? So in my first example, this highlighted blue area that I'm using are all values that are less than 0. So that means my answer are the corresponding x values that go with that. So the corresponding x values are any of these orange values. So those are from 1 to 5. So therefore, any x values from 1 to 5 would fit that solution. Again, when I'm solving, I'm not looking for ordered pairs. I'm looking for which x values make the statement true. Before, we used to just focus on the actual crossing of the x-axis, right, the ordered pairs. But now there's a variety because it's not just equal to 0, it's what's less than 0. In the second scenario here, again, I'm asking when is the equation less than 0? So I look at my graph, and where is that parabola? Again, less than 0 and in the negative range. It's highlighted on this blue area. Now, parabolas go on and on. So the x values that correspond with that blue area are the orange ones. So notice those are values less than 1 or greater than 1. The same thing goes if I wanted to talk about if I'm greater than 0. If I'm greater than 0, then instead of looking at below the x-axis, I'm looking at above. So I care about being in that positive range area and which x values correspond with that. Or in the second one here, being positive is above the x-axis, so I'd be focusing on the x values that correspond with the blue. So let's look at some examples. I will do number 3, and then you can try number 4. So if we look at this one, we're going to graph. So it's in standard form. So we find our axis of symmetry. X equals negative b all over 2a. So this gives me negative 5 halves. At that point, we can plug that into my equation or inequality. And we will simplify that. So I'm just going to plug it all into the calculator. I get negative 5 halves squared plus 5 times negative 5 halves. And then minus 6. And this gives me negative 12.25, which of course is the same thing as negative 12 and 1/4. So my vertex is negative 5 halves, or negative 2.5, and negative 12.25. That's going to run off the graph a bit, but that's okay. We can still do that. Negative 2.5, and here's negative 11, so we're down here. This one isn't so pretty to graph. However, the other thing you can do to help graph is I clearly can see what these roots are going to be, right? What are the roots going to be? If I factored this, I would get x plus 6 and x minus 1, which gives me roots of negative 6 and positive 1. So I can also plot those to help me graph, negative 6 and positive 1. And now I can connect that curve. So that's another way, if you get a nasty fraction to then go up 1 over 1 and so forth, the idea would be to figure out where those roots are easily by factoring. So now I'm just going to connect this. I can use a solid line. And I apologize that the curve isn't too smooth. What I'm focusing on isn't necessarily the shading and so forth. That was when I'm graphing. When I'm solving, what I'm focusing on is when am I less than 0? So when is this graph below, and I'm going to write that, when is the graph below the x-axis? Right? AKA, when is the range negative? So if we look here, I'm going to highlight that, right? It's all of this orange part. Anything down here has a y value that's negative and will be less than 0. So what are those x values? Those x values are between the two roots that I had. So I'm going to really bold those. We had negative 6 and we had positive 1. So my solution is going to be x such that x is between negative 6 and negative 1, or positive 1. Notice here, I included the equals to because our original is less than or equal to. So I can equal 0 when I am at negative 6, and then anything in between negative 6 and 1, and again, at 1 I'm equal to 0. So there is my solution. If I asked for when would I be greater than, then it would be the values above, which would be all x values less than negative 6 and all x values greater than negative 6. Okay, so again, when you're solving by graphing, The key thing is you want to know where those roots are, and sometimes they'll come out super nice just based upon our transformations. Other times you may have to find your vertex and then factor a bit to find those roots. Once you have that graph, you're focusing on whether you need to be looking below the x-axis or above the x-axis. Okay, give number 4 a shot. Now we can solve by factoring. So when our parabolas aren't as sort of pretty to graph, then solving by factoring and algebraically is easier. When the graphs come out pretty nice, where the roots pop up really easily, then making a quick sketch of a graph is totally, I'd say, the way to go. But if we think about it, not everything graphs nicely, right? We've seen that in the past. So our other option is to solve algebraically or by factoring. Now, if we can't solve by factoring, so I'm going to actually add a couple things in here. Oh, it is here actually. Then you can complete the square or use the quadratic formula. So solving quadratic inequalities by factoring / algebraically. Okay, because if it's not factorable, we'll use the quadratic formula or completing the square. So here's what we want to do. You want to start by factoring. And in order to factor, we need to make our equation, or in this case, inequality equals 0. So I'm going to add 14. Now I will factor. So what multiplies to 14 adds to 9? We get x plus 2 and x plus 7. That gives me roots of -2 and -7. What we know now is that my answer is either going to be, and I'm going to erase this afterwards, but my answer is either going to be x such that x is between those two values, or it's going to be x such that x is less than -7, or x is greater than -2. One of these will be my answer. Because I know my roots, now I need to know, am I below the x-axis, in between, or am I below the x-axis when I am on the outskirts? Okay, so if we solve this algebraically, I'm going to erase that now. What we're going to do is some test points. Okay, so if I solve it algebraically with the test points, what I'm going to do is literally pick a couple of points on the outside and inside of these two values. So one test point I'm going to use is going to be -3. -3 is in between these two values. Okay, so if I take -3 and I plug that in, we're going to have -3 squared plus 9 times -3. And you can use the original, or you can use once you solve for 0. It's up to you. And we're going to simplify that. So this is going to give me +9 minus 27 plus 14. And that's -4. So is -4 less than 0? Aha, it is. So what that means is that -3 is a solution, right? It's asking us what x values are going to make this less than 0, and -3 did. So what that's telling me is that -3 is in between my two roots, so that means my solution will be x such that x is in between the two roots. If I got a false statement, then it would be the other scenario. It would be that x has to be less than -7 or x has to be greater than -2. So your test point can be anything. It can be in between the two. It can be on the outside. You can pick a nice value like 0 to make life easy on yourself. But you need to make sure you analyze to understand. Okay, so since again, we got a true statement, -3 is part of the solution, -3 is in between my roots, so that's why my solution should be all the values in between the roots. Another way we can check that, okay, and I'm just going to do it right here. Another way we can check that is if we think about those roots, right? Here's my -2 and -7, and I think about this quadratic, it's a positive, so that means it's opening up, right? Who knows where the vertex is exactly? But I have my two roots, and it's a quadratic that's opening up since it's positive. So if I look here, I want to know which values are less than 0. Which part of the graph is below the x-axis? It's this part. And look at those highlighted blue values. It's between the two zeros. So again, my answer makes sense. Okay, so sometimes I use a combination of graphing and factoring to help solve. All right, I'll erase that so that you have space to solve after. Now let's look at number 7 together. So number 7, if I look at this, saying x squared is less than -8. Well, if I solved this by factoring, right? Factoring would mean to move this over and factor. Can we factor that? No, it's not factorable. So what's another way that we could solve these roots? We could use the quadratic formula, we could complete the square, or I can go back and I can notice here, I could take the square root since that x value is already alone. This will give me x is less than or greater than when I flip it, but we're going to get a plus or minus I root 8. Tell me about this situation. This is saying the graph never crosses the x-axis, right? AKA, there are no real zeros. There's only imaginary ones. So when I'm solving this, we're trying to think about when is my function, I go back to right here, when is this function less than 8? Well, think about what it's telling me by getting that imaginary. It's telling me I have a special case here. I'm not actually getting any roots. So those special cases is either that there's going to be no solutions or there's going to be an infinite amount of solutions. When I look at this here, I know that this graph, right, if I made a little quick sketch, this graph is at the parent function, is at the origin and moved up 8. So it's looking something like this. The question is saying, when is that graph less than 0? So when is this graph below the x-axis? Never. It's never below the x-axis. It's never less than 0. Therefore, what my solution is that there will be no solution. Okay? This quadratic function will never be less than 0. If the question had said, when is it greater than 0? Again, we would get imaginary answers. However, it would be all real numbers because anything above the x-axis would be positive, so everything would fit. Okay? So keep that in mind when you are solving algebraically. If you get roots, fantastic. Analyze with the roots. However, if you get imaginary solutions, that's going to mean it's a special case. So you need to kind of think of the graph and think about, am I below like it's asking me to be, or am I above? Okay, try number 6 and number 8. Both of these I think are factorable, so that'll be really nice for you. If they're not factorable, you can use the quadratic formula. And then after you complete those, give the sort of bonus one a shot. The nice thing about this is that it's already in factored form, so finding the roots is really straightforward. All right, and we will discuss this tomorrow in class.